If you're like me, sometimes you like to look up and glance at the stars, have yourself an existential crisis because the universe is so large and you and I are so small and we are all hurling towards oblivion, and it's fine. But I got some good news for you. The universe is even larger than we think. Now, just how can that be when the universe is already infinite, you might ask? See, it's expanding. I should note that all this following information is courtesy of the late Stephen Hawking's A Brief History of Time, a very good, albeit somewhat confusing bit of reading. This is all found in Chapter 3, The Expanding Universe. Go figure. Yeah, so our already presumably infinite universe is expanding. You might already know that if you've ever been particularly into cosmology. It's almost common knowledge that the universe is expanding and has been since the Big Bang. We can thank Edwin Hubble for that. Not that Edwin Hubble was single-handedly expanding the universe, but that he discovered it. But the first thing he did was establish there even were other galaxies, which he proved in 1924. He did this using a lot of measurements, working out the distances to 9 different galaxies. As Hawking put it, we have certainly come a long way since Aristotle when we thought that the Earth was the center of the universe. Yeah, sorry guys, we're not special. Our sun is just an ordinary, average-sized yellow star hanging out in one insignificant spiral-shaped galaxy located in an infinite universe. You want me to learn quantum mechanics? Actually, the literal next thing this book goes into is quantum mechanics and Heisenberg's uncertainty principle, so maybe I spoke too soon. Anyways, let's go into more how exactly Hubble realized the universe is expanding. It's truly quite interesting, and one of the concepts in this book that I actually think I understand very well. Stars. They're so far away, they just seem to be pinpoints of light. For a lot of stars, the only thing we can observe about them is their color. By focusing a telescope on a star, we can observe the spectrum of the light from that star, similar to Newton's whole light prism rainbow thing. You know the one. Yeah, that guy. We can learn a lot from the spectrum of a star, such as its temperature and even exactly which elements are present in the star's atmosphere. Okay, now let's talk about the Doppler effect and then how all this connects together into an existential crisis. You might know about the Doppler effect. I feel as though we've touched upon it in 8th grade, but if you're like me, you've blocked out the memory of 8th grade, so here's a refresher. Visible light is found in the form of waves. The different wavelengths of light are what we see as different colors, with red being the longest wavelength down to violet being the shortest. Funny, because on the entire light spectrum besides visible light, longer than red is infrared light waves, and shorter than violet is ultraviolet. It be like that sometimes. So now think about how we receive light waves and how the Doppler effects might come into play. Suppose a light source is moving towards us. When the source emits the next wave, it will be nearer to us, so now the distance between those two wave crests is smaller than if it were standing still. Here's an illustration of the same concept but with sound waves. Which is why when we hear cars or ambulances zooming past us, it seems to end up as a lower pitch moving away from us. And the exact same thing can apply to light waves. Stars moving away from us will have their light spectra shifted towards the red end with larger waves, and stars moving towards us will have their light spectra shifted towards the blue end with smaller waves. We just call those red-shifted and blue-shifted stars/galaxies respectively. You might see where this is going. Edwin Hubble was out there doing his galaxy color spectrum thing, and he realized that most galaxies appear to be red-shifted. Nearly all of them are moving away from us. But wait, there's more. The size of the galaxy's redshift, or how much it's shifted, is not at all random. It is directly proportional to the galaxy's distance from us. So basically, the farther a galaxy is, the faster it's moving away. So getting farther, but every time it gets farther, it gets farther. This was then coined as Hubble's law. Okay, the universe is expanding. What does this mean for us? This leads to questions about things such as, is the universe going to keep expanding forever or just implode on itself one day as a big crunch, or what? Well, there's basically 3 possibilities. The first one is that the universe just expands forever. Gravity can never stop it. The second one is the big crunch, in which gravity can make the expansion slow down and eventually stop. The galaxies will start to move towards each other and we get a reverse Big Bang kind of thing. The third solution is that the universe is expanding just fast enough to avoid implosion. Avoiding implosion is always good. So the speed of expansion starts to decrease but never reaches 0, like a horizontal asymptote, if you will. The present evidence suggests that the universe will probably expand forever, or at least the big crunch won't happen for another 10,000 million years. That's okay though, because our sun will have died and so will the solar system and mankind unless we found a way to colonize the other star systems. So don't worry about it. Focus on the short term, like that science test you've got tomorrow. Yikes. So that concludes today's episode of Crash Course Cosmology. Again, I wholeheartedly recommend Hawking's book, A Brief History of Time, available online as free, possibly illegal PDFs, or found in a local library near you. At least it will be as soon as I return this copy. And I'm certainly not done with it just yet, so stay tuned.